Okay, so guys, I'm going to trust, maybe I shouldn't. Let me make sure because I don't have any way to verify that this is the case other than to look. Okay, I'm going to trust that this is working. So today, guys, what we're going to do is we're going to start a 2-day conversation. I understand that none of you print the notes, right? All right. So if you had printed the notes, what you would actually have in front of you is both days of notes. Because Friday is going to be Wednesday continued. In addition to that, the homework assignment that you see associated with today, you will only be doing that portion of it which you can do. When I originally wrote this material, I tried to jam all of this into one big day, and it proved to just be inappropriate. You'll find out why in a minute. And so consequently, guys, we are going to separate this. We are only going to count it as one assignment. So when I see you on Friday, we're not going to grade homework. Well, maybe we will. We'll see. But we're just going to count it as one assignment. So guys, the question is, what are we going to do today that's this big? And the answer is this. Don't write it down. But it should sound familiar, right? So guys, this is the way we ended the last class period. We solved this equation. We figured out that when a mole of methane combusts with 2 moles of oxygen as it produces 2 moles of water and 1 mole of carbon dioxide, we learned that this reaction has a delta H of negative 890 kilojoules. And so we talked about some things. First of all, we talked about this. What does it mean that it's negative? It's exothermic. Then we talked about, actually prior to that, we talked about delta H. What does delta H stand for? Change in enthalpy, because we found out that heat is Q. Hang on, guys. Hold on. We found that heat is Q, and we learned that enthalpy is H. And so now we understand that enthalpy is heat in the absence of work, and we learned that this reaction gives off this amount of heat as it's written. We also learned this. What if we were to switch the arrow and run the reaction in this direction? What happens? The sign changes and it becomes endothermic to the same extent. Brandon, I'm about to move you. It becomes endothermic to the same extent. Guys, and then the other thing that we talked about is this. What if we were to go back and say how much energy is released when 2 moles of methane combust? Twice as much. So guys, we talked about all these ideas. What we didn't talk about is this. Where on earth do these numbers come from? How do we know that this is the case? And guys, that's what we're going to talk about over the next 2 days. We're going to talk about where do these values come from that we use as the enthalpy changes for reactions. Now guys, you know that I'm all about organization, and I think you'll benefit from this as well. Guys, here's the question we're asking, and you want to write this down. If we've got some reaction where some X plus some Y yields some W and some Z, we've got this delta H value. Typically they're in kilojoules. And typically, guys, they'll always have a sign. If it's negative, it's exothermic. If it's positive, the positive sign is assumed to be there, and we know that it's endothermic. But guys, the question that we're asking is this. Where do we get this enthalpy data? Now guys, the answer is 2 places. Sometimes we'll get this enthalpy data empirically. What does that mean? From lab. And guys, when we do, there's a name for that process. It is called calorimetry. But guys, interestingly, there's another way that we can come up with this information. There's another way that we can figure out enthalpy changes for reactions. It is through a process, forgive the term, but through a construct that we call Hess's law. Which was a lot more fun to teach when the Hess kids were coming to Orem High. Do any of you know the Hesses? Isaac Hess, Ryan Hess. Their dad, Nathan Hess, he's actually, their dad is a physics professor at BYU. And it was much more fun. Kind of like Super Nate, only different. So, guys, when we talk about Hess's law, what you're going to find out is that Hess's law can be dealt with two ways. It can be addressed through what we call manipulation, and then it can be addressed through what we call computation. Which reminds me, I need to make copies of the AP equation sheet for you guys. That'll work. Okay, so guys, I don't expect this to make sense to you other than this. You got to understand that what we're talking about is where does delta H come from? We now understand that you can figure it out through empirically through the lab or through something called Hess's law. So guys, here's the way this is going to go down. This is what we're going to do today, and this is what we're going to do on Friday. Okay? So what you're going to see, guys, is that you have got to be responsible for all three of these ideas on the AP test. They will have you figure out delta H values through calorimetry. I don't know if I've shared this with you or not, but now one of the things that we can be assured of on every AP test is that there will be a lab. Understand that if you're not in lab, you are at no disadvantage, because the only difference between a lab question and all the other questions is they show you a diagram of the apparatus, and you guys will understand the concepts behind it and you'll be fine. But there will always be a lab question on the test, and that could be a calorimetry question. We haven't seen a calorimetry question since the rewriting of the test in 2014. So it may be this year, well, next year. But then, guys, they will also have you figure out delta H values through manipulation and computation. And we'll talk more about this on Friday. How do you know which approach to use? And we'll figure that out then. And actually, this is fun for me to teach because I figured out a great way to help you figure out the difference. So, guys, today what we're going to do is calorimetry, and then after that, we're going to talk about these other two ideas. We'll do that Friday. Used to do this all in one day. It was a whopper. Now we're going to separate them out. You guys ready to go? Okay. So, guys, with that said, we need to set some background for this. And so this, frankly, is just stuff that you've got to write down. So how do we deal with heat? Well, guys, why is it that we're now talking about how to deal with heat? What about the other way of getting energy in and out of reactions? It gone. Guys, we're not going to talk about work anymore in this class. And this could create some confusion. So guys, let's make sure you're clear, because as a chemist, and you guys are chemists, as a chemist, you will find that chemists talk this way. And it's sloppy, but it's okay. So guys, here's the idea. How do you get energy in and out of a system? Work and heat, right? How do we get rid of work? Constant pressure, open containers. When we get rid of the opportunity for work, we're left with heat. And what do we call heat in the absence of work? Call it enthalpy. But what you're going to find out, guys, is that chemists tend to get sloppy about this. And for example, if you see a chemical reaction like the one we threw up on the board, X plus Y is WZ, and delta H has got some value, you'll hear a chemist say the enthalpy change for this reaction is. Or you will also hear them say, the heat of this reaction is. And we're thinking about the same things. So because so many times in chemistry we just assume that work is negated and we're only talking about enthalpy, a lot of times you'll hear chemists use heat and enthalpy interchangeably. Understand technically they're not, but you'll hear me talk a lot about heats of reaction. What we're really talking about is enthalpies of reactions, because we just all assume that work is not on the table. Okay, so with that said, guys, how do we deal with heat? Understanding what we're really talking about is enthalpy, because we've already gotten rid of work. You okay? Okay, so how do we deal with heat? Well, guys, there's a couple of ways we can do this. One of them is what is called molar heat capacity. And I should tell you, guys, this is not an exhaustive list. These are the ways to quantify heat in AP Chem. There's lots of others. This is the way we're going to talk about this. Or I should say that differently. These are the only ways we need to talk about this, because this is what they've done in AP Chem to limit our options. So guys, molar heat capacity is defined as the amount of energy needed to raise 1 mole of a substance's temperature 1 degree Celsius. That's probably a definition worth writing down verbatim. Did y'all get it? So let's talk. Guys, what are our units for energy? Joules. Now here we've got moles, and understand the abbreviation for mole is just MOL. And then we've got degrees Celsius. So this is the logic behind it, and write it down with me. The molar heat capacity tells us how many joules of energy does it take to raise 1 mole of a substance's temperature 1 degree Celsius. So guys, the units for molar heat capacity, which are contained right in the definition, is the amount of energy in joules per mole Celsius degree. So guys, those are the units for molar heat capacity. They are joules per mole Celsius degree. You'll also see that written like this. Did we already talk about this? That the -1 pushes it into the denominator? But now, guys, and this is important because this is going to get a little funny. Well, not funny. You got to know the abbreviation. You could even, I mean, you really don't need to write out the sentence. But guys, this is abbreviated capital C sub M. The molar heat capacity. The C is for capacity. Got it? Okay. Now, guys, let me just ask you, I suspect some of you had this experience. When you wrote down the definition of molar heat capacity, did it sound familiar? What did it sound like? Do any of you know? Do you know, Kimmy? Okay, so there is another way of thinking about this in terms of grams, but it even becomes more specific. Do you know? The calorie. Guys, the definition of a calorie is the amount of energy needed to raise 1 gram of a substance's temperature 1 degree Celsius. I don't know if you knew that. But guys, that is actually in reference to what we call specific heat capacity. Or you'll hear people just call it specific heat. And this then is the definition that you're more comfortable with. Bless you. The amount of energy needed to raise 1 gram of a substance's temperature 1 degree Celsius. And so I don't think I have this in my notes, but because I think some of you are familiar with it, we could at least write it down when you're ready. So what is the specific heat of water? 1 calorie. So guys, when our substance, and this isn't really as I said in my notes, but when the substance is water, the specific heat is 1 calorie. And that would be 1 calorie per gram Celsius degree. Or you may remember we talked about the conversion. 1 calorie is equal to 4.8 joules per gram per Celsius degree. So the specific heat of water is 1 calorie or 4.18 joules because those numbers are the same. Because a calorie is the same as 4.18 joules. So all of that then to say, can I get rid of this? Oh. Got it? Okay, so guys, all of that then to say we understand that the units for this are joules per gram Celsius degree. But this is important. On the AP sheet, this will either be abbreviated big C sub S, or it could be abbreviated little c. But what you're going to see is on the AP cheat sheet, it's this. Specific heat is abbreviated little c on the AP test, or on the AP equation sheet. Yeah?
Is that a calorie though?
No. Because we won't be using calories, we'll be using joules. And as a result, we don't have to draw the distinction. Yeah, understand, as you get deeper into science, there's so much overlap in terms of abbreviations that it just gets squirrely. But because we'll never use energies and calories, we'll always use joules and kilojoules, we don't have to worry about that overlap. Okay, you guys okay? Okay, so guys, with this as a framework then, let's move on. And let's start then talking about how it is that we are going to quantify amounts of energy. And again, guys, are you okay with this idea? I should do this in a way that's not, well, I just need to get to there. So guys, today what we're going to do is we're going to talk about the empirical collection of energy data. Okay, how do we know how much energy a reaction loses or how much heat a reaction loses or gains? Again, assuming no pressure, so therefore no work. How do we do this empirically? How do we do this in lab? And that's where we're going to stop today. You ready to go? Okay. So guys, when we talk about this, what we are talking about is a process, again, called calorimetry. Now, guys, as calorimetry applies to this class, all you need to know is about this. So guys, please don't write, just watch. Guys, it used to be that in AP, you had to be familiar with multiple types of calorimetry and understand you could actually become a calorimetric chemist. Dr. Brown, the guy at BYU that used to run the freshman chemistry lab, actually was a calorimetric chemist. He retired, but he spent his entire life, his research life, trying to figure out the energy changes in reactions. It's a fascinating and broad subject area. Guys, all you've got to know is this. With the understanding that in Utah County, this is lost on many, but this is actually what is called coffee cup calorimetry. You can use that term, and if you were to talk to a chemist and say, hey, set up a coffee cup calorimeter, they will immediately know what you're talking about, even if it's not in a coffee cup. And guys, we're not going to use coffee cups. I actually bought better containers than coffee cups, but you can actually build a pretty stinking good coffee cup or calorimeter by taking 2 coffee cups and stacking them together. But guys, this is actually what is called a constant pressure calorimeter. So guys, when we talk about constant pressure, what's the tie back into this? If it's constant pressure, it's got to be enthalpy, because what can't happen? Work. Okay, so guys, here's what you're then going to do in your notes, because this is where we're going to wrap up today. So guys, what you need to do in your notes is just write down coffee cup calorimetry, which technically is called constant pressure calorimetry. Then stop. Okay, so now guys, let's talk. What I want to do is I want to give you just sort of a tour, if you will, through this schematic drawing. We'll talk about the pieces and the parts. Then what we'll do is corporately, I'm going to just put a white overlay over the top of this, and we are going to draw a stick drawing of a coffee cup calorimeter, and then we're going to get into the chemistry and the logic and the math of coffee cup calorimetry. But guys, as you can see from a distance, coffee cup calorimeters are really simple systems. And I should be careful with system. You're going to find out in a minute that's not a good term. But guys, functionally, all that we've got is a couple styrofoam cups. If you were to buy a really good constant pressure calorimeter, it actually wouldn't be styrofoam cups. It would actually be like a what? Exactly. It would actually be like a hydro flask. And I don't know if you guys understand how these work, but this is why they're so stinking expensive. Guys, you understand that the inside and the outside don't touch? Yeah, this isn't one layer. That's actually what's called a vacuum flask. And so the outside and the inside are separated by a gap. And what's in that gap? Nothing. And because there's nothing in that gap, they draw a vacuum on it before they weld the thing together. It turns out that heat has a hard time radiating from the inside to the outside because heat radiates best through contact. And if there's nothing in between, a vacuum to create transfer, the heat tends to stay put because it can't get out because there's nothing for it to transfer through. That's why these work so well, and also why they're stupid expensive. So, guys, the way that we build them then is we allow there to be contact, but we use styrofoam, and we allow the styrofoam to touch because it doesn't transfer heat very well. It's a pretty good insulator. Then what we do is we put a lid on this bugger because we don't want heat getting out the top, and then inside of a calorimeter you functionally have two things. You've got three things. You've got a thermometer, you've got water, and then you've got a stirrer. And guys, and in a real coffee or in a real constant pressure calorimeter, the stirrer would actually be mechanical. You flip a switch and this little impeller stirs the thing. When we do this in lab, instead of that, what we'll do is we'll actually take a loop of nichrome wire. We'll basically do this. We'll take a piece of nickel chromium wire and we'll throw a loop on the end of it, and then we'll thread our thermometer through it. And then what we'll do is we'll slide that up and down our thermometer and we'll use that to stir. The reason that we do that is then we only have to poke one hole in the lid and it keeps heat transfer down. But in either case, you need something that stirs. And then guys, you'll notice that here it also mentions that there's a sample, and it shows you a block as if the sample's got to be a solid. You're going to find out in a moment that many times the thing that you're studying is not a solid. Although in the lab that we're going to do not next, but the time after, your sample will be a solid, and we're going to figure out what happens when it dissolves. But for now, understand your sample does not have to be a solid. So you guys kind of get the ideas? You're good? Okay. So when we set these up in lab, our lid is not going to be a lid. It's actually going to be a piece of cardboard. And we will, in fact, put a thermometer and a stirrer in that, and we'll set up something like this. You good? Okay. So with that said, let's draw ourselves a model of what we're talking about. So guys, and you're going to want to leave. You want to draw this big enough that you've got room that you can sort of write inside the calorimeter, but it's going to be really important for you to leave white space around this because this is going to get nasty because we're going to be just brainstorming all around this thing. So you're going to need some space. So guys, I'm going to go with black. I got to sort of picture this. So I'm going to go coffee cup, and I'm going to go lid, and I'm going to go water, and I'm going to go thermometer. I'm going to move that over. Well, how am I going to do this? No, that's okay. So I'm going to go thermometer and then the stir around that. That's horrible, but it'll work. This is what happens when you have zero artistic skills. So guys, this is up to you. I would encourage you not to, but it's up to you. If you want to label the parts, you can. My fear is that labeling is just going to create more clutter. But you're probably okay with coffee cup, well, insulated container, coffee cup, lid, thermometer, stirring thing, and then water. So if you need to label them, I'd encourage you to do that conservatively, but you're certainly welcome to if you need. You guys okay? Okay, so guys, what we're going to do now is this. These are the things that you need to understand about calorimetry, about coffee cup calorimetry, when this is all over. So the things that we're going to talk about is this. The first thing we're going to talk about is the usefulness of coffee cup calorimetry. Then what we're going to do is we're going to talk about when we do coffee cup calorimetry, we're going to talk about defining the system. Then once we understand what the system is, we're going to have a conversation about heat. And then once we understand the way heat is being exchanged within this apparatus, we are going to talk about the math of how we're going to understand or how we're going to calculate the data that this provides. And so maybe this would say not just heat, but heat and maybe, I don't know, logic's not the right word, but I can't think of a better one right now, so we're just going to use it. So guys, now that you sort of have a sense of this, lights on or off? Are you guys okay to write? You're okay? Okay. All right, so guys, switching colors. You guys all caught up with me? You ready to roll? Okay. So guys, the first thing that we need to talk about is when do we use coffee cup calorimetry? And the answer in AP is always, because it's the only one you need to know. But when do we use coffee cup calorimetry if we had other options at our disposal? Well, guys, I think you can actually already figure out the answer. Does anyone see it? Guys, what kind of chemistry let me say this differently. What is the only kind of chemistry that you can do in a coffee cup calorimeter? It's got to be aqueous chemistry. Guys, the only kind of chemistry that you can study with a coffee cup calorimeter is aqueous chemistry, because there's got to be water. A coffee cup calorimeter without water is not a calorimeter. Guys, understand there's lots of other types of calorimetry that you can use to study non-aqueous chemistry. We're not going to worry about it. The only one that we need to worry about is this, and that always requires aqueous chemistry. So guys, with that said then, here's the trick. When we do calorimetry, regardless of the type, but when we do calorimetry, guys, the key to success with calorimetry is to very, 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 very carefully define your system. And I'm not going to allow you to guess at this because it's only going to create confusion. I'm going to tell you right up front, what is the system in coffee cup calorimetry? And guys, the answer is this. The atoms of reactant and product. That's it. In coffee cup calorimetry, the system is the atoms, are the atoms. I don't know if that's plural or not. The system's the atoms. So guys, if that's true, what does it then make the entire stinking calorimeter? The surroundings. Guys, you've got to understand, and this is where this gets a little complicated, but you've got to understand that every stinking bit of that calorimeter is the surroundings. So now maybe we should talk about that. So we've got this idea of what the system is. I think it might be worth doing this. Let's put a finer point on what the surroundings are. Because guys, this is going to be helpful for us. We've got this elementary idea that universe minus system is surroundings. But guys, what you're going to find out is that we can do a little bit better than that. So guys, now let's talk about in coffee cup calorimetry, what are our surroundings? So what are the parts of the calorimeter that we are going to include as our surroundings? Well, ready? Guys, it goes like this. The cup is part of the surroundings. The water is part of the surroundings. The lid is part of the surroundings. The thermometer, part of the surroundings. The stir is part of the surroundings. But guys, what about the rest of the universe? Didn't we say that once we identify our system, everything else is the surroundings? Guys, what is it that allows us to limit our surroundings? Because up until now, we've had this idea that the surroundings are limitless. Once you've got the system, the surroundings are everything else. And while functionally that's true, guys, what is it that allows us to say in this instance that our surroundings are not everything, it's more limited? What lets us do that? Go ahead. Tell me more. I love the word. Tell me more. What do you mean by proximity? Okay, so I love where you're headed with that, but let's talk about some other parts of the universe. We've got oxygen and nitrogen and carbon dioxide and all the other parts of the world here. And this thing will be sitting on a desk. And that's also, don't write these down, that's also part of the surroundings. But it does come back to proximity. What is it that allows us to exclude the air and the desk? The container. Guys, the idea is this. Because we are using an insulated container, what we are allowing ourselves to do, and you may want to write this in with me if you don't understand the logic. I'm going to switch to a horrible color like yellow. Because this is an insulated container, physically what we're allowing this to do is insulate the rest of the surroundings from the part of the surroundings that we really care about. You understand how that works? But guys, understand this. Does it really work? Even if they're doubled up, do two styrofoam cups really separate everything that's inside the cup from everything that's outside the cup? You ever gone and got a cup of hot chocolate on a cold day and it's in your happy little styrofoam cup and you got your hot chocolate and you can barely drink it and then you set it down and forget about it and you come back an hour later and it's disgusting because it's room temperature? You know what I'm talking about? So guys, does that styrofoam cup truly insulate the contents from the surroundings? It doesn't. So understand that, and we're going to talk about how to account for that later, but understand, and I love your term proximity. Guys, we do have proximity issues. We've got the rest of the universe packed in around this calorimeter, and we understand that the coffee cup slows the transfer of energy to the universe, but it doesn't fully prevent the transfer of energy to the universe. Over time, we're going to lose energy, right? So what does that mean we're going to do in lab? Work fast. right? Because the faster we can collect our data, the less energy we're going to bleed to the universe, the real universe. But guys, actually you're going to see there's another thing that we can do that's pretty tricky too, that will allow us to mathematically compensate for the loss of energy through the cup, but we'll talk later. So guys, here's what we're now saying. Just one second. What we're now saying is our system are the atoms, our surroundings we are going to limit just to the cup, the water, the lid, the thermometer, and the stirrer. Again, the thing that allows that is the insulative nature of the cup. We understand that it doesn't truly separate, but it separates well enough that the model works. You get the idea? Go ahead. Yeah, and that's a good question. The thing that's really cool, and I'm going to use this term with you, the specific heat of air is frighteningly low. Air is not a good heat sink. It doesn't hold energy very well. So the little bit of energy that we'll lose to the surrounding air that's trapped under the lid is so minimal that technically we should account for it, but it would round off if you do significant digits. It's really low. Gases have ridiculously low specific heats. So, all right, so guys, you good on the idea? So how then does this work? Let's talk about the transfer of heat and let's talk about the logic behind the process. Well, guys, as we said initially, the chemistry that we do inside of coffee cup calorimeters is aqueous chemistry. So think about everything that you learned in the last unit. When we think about aqueous chemistry, we think about acid-base reactions, we think about precipitation reactions, we think about gas-forming reactions, we think about redox reactions. And all of those reactions we can study the energy of in a coffee cup calorimeter. So guys, how do we do it? Well, check this out. Let's do neutralization first. So guys, draw small, but do this with me. Say that we're going to, oh, not that color. That's like vomit yellow. So say, guys, we are going to get a beaker of hydrochloric acid and a beaker of sodium hydroxide. And we want to know when sodium hydroxide reacts with hydrochloric acid, how much energy does it give off? So guys, here's the way we're going to do the chemistry. Ready? What we're going to do, and it doesn't matter which one, we're going to set up our coffee cup calorimeter. Imagine that it's now empty. And again, it doesn't matter which one. We're going to dump one or the other of these in here. So say that this was initially empty, and then we went bloop, and we dumped in the sodium hydroxide. So now we've got sodium hydroxide in our calorimeter. Now guys, here's what we're going to do next. Once we've got that in there, we are now going to dump the HCl in the calorimeter. And guys, what's going to happen? They're going to react together, right? So if you'd like, if it's helpful, we can figure out the products. Table salt and water, with the understanding that the sodium and the chloride ions are spectators, and the net ionic equation is hydrogen plus hydroxide makes water. You okay with that? But here's the thing that's also going to happen. This gives off a bamboozle of heat. This is a frighteningly exothermic reaction. So as the atoms, sodium chloride, hydrogen, oxygen, sodium chloride, hydrogen chloride, sodium, oxygen, hydrogen, as these atoms react together, as they form bonds, they give off a lot of heat. Here's the question. Where does the heat go? Okay, let's track it. Do this with me. So draw yourself a box around your reactants. That's your system. You just drew a box around the system. Now, This is exothermic, so heat's going to go out. So where does the heat go? It goes into the water. Where else does it go? By the way, maybe we should ask this question. Where did the water come from? The acid and base were dissolved in it initially, right? Okay, so the energy goes into the water. Where else does it go? Into the stirrer. Where else does it go? Into the thermometer. Where else does it go? Into the cup itself. But here's the trick, guys. Where does most of the energy go? Into the water. Guys, water has such a high specific heat that many times it's reasonable to just say the energy was absorbed by the water. Because the amount of energy that the glass thermometer, the metal stirrer, and then the insulative cup absorbs is very, very small. You're going to see in lab that we will actually quantify it when we calibrate our calorimeters. But guys, understand that most of the time in the class, they'll just simply say, assume that all of the energy was absorbed by the water. We can quantify the other, but typically we don't have to worry about it. But guys, the idea then is that when the energy is lost, and we're going to write this here, I'm going to need to make a little bit more room. So guys, when the heat is transferred, the idea is this. The heat is lost by the reaction, and it is gained by the water. Understand, we get that, yeah, a little bit of energy goes into the glass, the thermometer, the stirrer, the cup. But guys, for the most part, this is true. Now understand that this is true if the reaction is exothermic. What if the reaction is endothermic? Energy goes the other way. Exactly. So the energy would be lost by the water and gained by the system, the reactants. But guys, what do we know about the amount of energy lost by the reaction and gained by the water? They're equal. Says who? First law of thermodynamics. Guys, that's the whole idea. Understanding that we really should account for the little bit of energy lost to the stirrer and things like that. But guys, we are going to say that this is not only directional, we're going to say that it's equal. The amount of energy that is lost by the reaction, if it's exothermic, the amount of energy lost by the reaction is gained by the water. Understand that if it were endothermic, the arrow would change, the direction would change, but they would still be equal. You get the idea? Okay, so now we've got to talk about the math. So guys, this is the way the math goes. Here's what we know. We know that the energy lost by the reaction is equal to the energy gained by the water. Do you buy that? Okay. Is that okay? Because that's critical. You agree with that. Is that okay? Okay. But now, guys, here's the problem. Remember when we said this last time in class, we can't directly measure energy? Remember that? Okay, so we said if we can't directly measure energy, what do we look for? Changes. And guys, in this particular instance, what is the thing that we are actually going to see change? The temperature of what? The water. And this then becomes the logic. Guys, we have an equation that will tell us how energy changes temperature. And the equation is this. Write this down with me. The amount of energy lost or gained, in this case by the water, is equal to the mass of the water, the specific heat of the water. Oh, I got to make sure. Hold on. How do they do it on the AP test? What was specific heat? Just C. Sorry. I learned it in college as CP, and they don't like that. So that's little c. And then, guys, delta T. So here's what that means. It means if we know the mass of the water and if we know the specific heat of water, which we do, 4.18 joules per gram Celsius degree, and if we know the change in temperature of the water, we now know how much energy the water gained. But guys, how much energy did the water gain? The same as what? The amount of energy that the reaction lost. Because guys, this value tells us the energy gain of the water. And that is equal to the energy lost by the reaction, again, assuming it's exothermic. And so guys, these are the same. So here's what we do. We set up our calorimeter and we dump in the sodium hydroxide and we measure its temperature. Then we dump in the hydrochloric acid, assuming the hydrochloric acid started at the same temperature. We dump them together and the temperature goes up. Why did the temperature go up? Because the reaction's releasing energy. And by measuring the amount that the temperature of the water goes up, we can plug that in here, figure out the amount of energy that the water gained, and that's equal to the amount of energy that the reaction lost. Does that make sense? So let's try it. Told you that was going to get messy. What? M is mass. C is specific heat. So guys, let's try this. The thing that's really cool to me is I've been doing this for what now, 15 years? More than that, 17. This slide never looks the same twice. I love that. It's always right, but it's always different. It makes me happy. So guys, let's try this. You already know all of this stuff. This is everything that's on your slide. There's the equation. We know system and surroundings. We've got all of that. Now let's try this. We're going to solve this together to wrap up the day. It says when a 3.25 gram sample of sodium hydroxide was dissolved in a calorimeter with 100 grams of water, the temperature did this. Calculate delta H for the process. Assume that it's a perfect calorimeter and that the specific heat of the solution is the same as that as pure water. So what does it mean that we can assume that it's a perfect calorimeter? That means that the energy is only going into the water and it's not going anywhere else. That's how they'll say that to you on the test. They'll say assume that it's a perfect calorimeter, and at that point you can assume that the energy is only going into the water. And frankly, those are the only kind of questions I've ever seen them pose on the AP test. In lab, you're going to find out that we will actually deal with the energy lost to the calorimeter, but on the test, I've never seen them have you account for that. So, you guys ready to go? So allow me, and you're welcome to join me if you'd like. It's helpful for me to draw a picture. So what does this look like? Well, guys, it looks like this. We've got some water in our calorimeter, and then we've got a chunk of sodium hydroxide. Now, guys, understand that that sodium hydroxide is a solid. We're not talking now about an acid-base reaction. We are treating sodium hydroxide as a salt. It's a solid, and we're going to dump it in water and let it dissolve. That's how it becomes a base. But what we want to know is how much energy is involved when that happens. So, guys, how much water is inside our calorimeter? 100 grams, right? Is it 0.0? Oh, good. So we've got 100 grams of water inside of our calorimeter, and we are going to dump 3.25 grams of sodium hydroxide into that 100 grams of water. When we do it, we'll dissolve, and energy will be taken in or given off by this process. So guys, let's talk. Question number one is this. What's our system? The sodium hydroxide. What's our surroundings? The water. What do we know about the amount of energy lost by the sodium hydroxide? Equal to the amount of energy gained or lost by the water. So now let's talk. Did the water gain or lose energy? How do you know? Temperature went up. It went from 23 to 32. So guys, think about it this way. Watch my hands if it's helpful. So we've got system, we've got surroundings. System is the sodium hydroxide, surroundings is the water. So what happened to the energy of the surroundings? Went up. So what happened to the energy of the system? Went down the same amount. So is this endo or exothermic? Exothermic. Because guys, remember, we are in the system. Yeah, the water gained energy, but the value for delta H is going to be negative. Because we're not talking about the change in energy of the water. That's the surroundings. We're talking about change of energy for the system, the sodium hydroxide. So, how do we know how much energy dissolving the sodium hydroxide gave off? What do we need to know? How do we know how much energy dissolving this gave off? It's the same as what? The amount of energy gained by what? The water. And how can we calculate the amount of energy gained by the water? We need an equation. We need Q is equal to MC delta T. So now, guys, let's do the math. We are solving for Q. What is the mass? 3.25, 100, or 103.25? What is it the mass of? The water. That's 100 grams. Why do we want the mass of the water? Because that's where the energy went. It went into the water. Now we need to know the specific heat of water. It's 4.18 joules per gram Celsius degree. And now, guys, we need to know the temperature change of the water. 8.1. Is that right? Can I do math in my head? 8.1 degrees Celsius. Now, guys, watch how the units cancel. This is handy. Celsius cancel, grams cancel. We're left with joules. Just like being there. Now, guys, let's do the math. 100 times 4.18 times 8.1. Okay. So, guys, here's what we know now. Q is equal to, what do we get? 2 significant digits? 3,400 joules. That's not the answer to the question. Guys, where did those 3,400 joules of energy come from? Sodium hydroxide. How much? 3.25 grams. So what we know right now is the amount of energy that's released when 3.25 grams of sodium hydroxide dissolves. That's not what the question is asking. The question is asking for the delta H of this process in kilojoules per mole. So guys, now we need to do some math. Can I write down here? Is that high enough? Or should I start a new page? Am I okay? Okay. So guys, what we want to know, what the question is asking us, is what is delta H in kilojoules per mole? And we don't know yet. What we do know is this. 3,400 joules of energy is evolved when we dissolve 3.25 grams of sodium hydroxide. We've got some calculations to do. So we've got to convert joules to kilojoules and grams to moles. But we can do that, right? So joules to kilojoules, 1,000 joules is 1 kilojoule. And then grams per mole, it's 23, 16, and 1 approximately. So 40.0 grams of NaOH is 1 mole of NaOH. So now we do this math. And we go 3,400 divided by 3.25 divided by 1,000 times 40. And we get 2 significant digits. So I get 42 kilojoules per mole. Just a moment. So guys, let me ask you a question. Could you imagine on the AP test going through this entire process and getting no credit for it? Because if you did this on the AP test as the answer to this question, you would get 0 credit. You want to know why? It's negative. This value is negative. How do we know? because we know what this represents. This is the amount of energy that is involved when sodium hydroxide dissolves. And guys, the water absorbed the energy. The sodium hydroxide, which is our system, gave it off. And when you're simply counting, just a minute, when you're calculating delta H, guys, you got to understand that direction counts. So let's do the pledge and then we'll wrap this up. Allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all.
We go to their classes, announcements will be using
Oh, guys, I printed my Pride report and my printer ran out of paper. Sorry. So let's wrap this up, and then if you've got an eye, I'll get you out of here in 2 seconds. So guys, understand it's got to be negative because this reaction, this process is losing energy, and that's important. Catherine, go ahead. No, sorry, this should be kilojoules. Sorry, yeah. Okay. You guys okay? Okay, so guys, let me...
This week is Zero Fatalities Week. Come join us in a little theater today during lunch. Tomorrow, NHS applications are due. It's only a day away.
Write these down and then we'll talk.
Math Cafe will begin today.